So in this video, I want to talk about a scenario where we have 10 marbles in some container in a bag or a box. And the idea is that we're going to select 2 marbles from this container, one marble at a time. And so what we're going to do is I'm going to let B1 and B2 be the events that we select a blue marble on the first draw or the second draw. And likewise, R1 and R2 are the events that we select a red marble on the first draw, or R2 will be on the second draw. So what I want to do is I want to think about what's the probability of selecting a blue marble first or a red marble first, and we'll make a tree diagram from here. So the way that this will work, there will be a few branches here. I can, in the first selection, I can select either a blue or a red marble. And then after that, on the second selection, we can select a blue or a red marble again. So it could be blue or red, blue or red. And what I'm going to put on each of these branches is the probability of each event happening. So the first time I'm going to do this without replacement. So that what that means is that whatever marble I select on the first round, on the first draw, I'm not going to put it back in the container for the second draw. So it's out of the game. So what we're going to do is let's start by thinking about the probability that a randomly selected marble is blue or red. And so there's 3 out of 10 marbles that are blue. So the probability that the first one will be blue is 3/10. Likewise, the probability that the first marble will be red is 7/10. Notice that those add up to 1. And now I want to think about each of these scenarios. So let's say that we draw a blue marble first. And if that's the case, let's remove it from the pile. And what's going to happen is now we have 9 marbles remaining. And we want to know what's the probability that we select a blue marble second in this scenario. So there's 2 of them of the 9 are blue and 7 of the remaining 9 are red. And then we'll do the same calculation but removing one of the red marbles. So if our first selection is red, then there will be a 3/9 or 1/3 probability that the second one will be blue versus 6/9 or 2/3 probability that the second one will be red. And what I want to do is I want to think about, let's just think about one of these numbers, say 7/9. And I want to think about what does that number actually represent. So what is 7/9? And it turns out 7/9, I'd encourage you to pause for just a second and think about what that 7/9 represent. But what it does is it represents the probability that the second draw will be red, given that the first was blue. So that 7/9 is really the probability of R2 given B1. B1 had to happen first in order for that R2 value to be what it is. So these numbers on the second, whatever you want to call it, second set of branches, these numbers here are all conditional probabilities. They're all probability of something given something else, probability of A given B or whatever. And so we can compute a few different things here. So that's the probability of R2 given B1. We can do a few other interesting questions along the way. Let's think about a few things here. Let's think about what's the probability of selecting, let me write this in a better order, of selecting a blue marble first and I can't draw our symbol here, our ampersand. So I want to know what's the probability of selecting a blue marble first and a red marble second. And it turns out that there's a few ways to think about this. One way to think about this, just to kind of reason it through, is that this is going to be the probability that we select a blue marble first times the probability that, given that happens, times the probability that we select a red marble second. So that's R2 given B1. And this follows right from the formula. We know what the formula is for the probability of A given B. So I think that this is worth remembering. Let me just write this off to the side here. So I just want to recall that the probability of A given B is the probability of A and B divided by the probability of B. Okay, so that's the formula that we have for the probability of A and B. All right. My squiggle is a little ugly here. All right. So that's a formula that we'll use over and over. That's our conditional probability formula. So the probability of B1, we've already established as 3/10. The probability of R2 given B1, we've already established as 7/9. And so altogether, that's going to be, let's see, 3 over 9 cancels, and this will be 7 over 30. 21 over 90 or 7 over 30. So that's the probability that we select a blue ball first and a red ball second. There's a few other things that we can talk about here. You can do all sorts of different varieties of this question. What's the probability that you selected a red ball and a red ball first and a red ball second? So you could do that. You could do that calculation. But let's do some other things. So what I want to do is let's look at a more interesting question. And what I want to know is what's the probability that we select a red ball second? And this is a more complicated question than it may seem at first, because there's a lot of different ways to get to a red ball. And well, in this case, there's two, but there's more than one. So you can either get a red ball by first selecting a blue ball, or you can get a red marble by first selecting a red marble. So there's two paths to get there. Let me get rid of this highlighted text here. And so there's two paths. And so the way I like to think about this is that if I want to know the probability of R2, I like to highlight, or I like to just think about what are the different paths to get there. So you could do, again, R2 having done B1 or R1 first. So there's two different ways to do it. So another way to write the probability of R2, another way to break this down, is that this is the probability. When you have a second marble being red, there's two ways it could have happened. It could be that the first one's blue and the second one's red, or that the first one's red and the second one is red. And notice that this is really an or statement, but these are disjoints. They're mutually exclusive sets. You can't do both of them at the same time. If the first draw is a blue, it can also be a red. So we can just add the probabilities and everything is fine. Now we can compute this and symbol, by the way. There should be an and. Trying to keep consistent with our notation from the book. And then we know how to compute these. The probability of B1 and R2, we've already computed to be 7 over 30. That's the computation that we did right above here. Okay, so that's the 7 over 30. The second computation is going to be similar. So it'll be 7/10 times 6/9. So 7/10 times 6/9. And again, the 6 over 9 simplifies to be 2/3. And so that's going to be 7 over 30 plus 14. Yeah, it'll be 2/3. So 2/3 of 7/10 will be 14 over 30. And so it turns out that there's a 21 out of 30, or 7/10 probability that the second marble will be red. Okay, and this is with replacement. This is without replacement, I mean. So this is what's going to happen when we don't put the marble back. So that's the story there. So let's pause, and then I want to do one more calculation here. So the last thing I want to do is I want to do this backwards. We've talked about how to find the probability of R2 given B1. But what I want to know is the following. I want to know what's the probability that the first marble that we selected was blue, given that I already know for some reason that the second marble is red. Okay, that's a slightly backwards way to ask the question, and that seems slightly silly in this case. But there's a reason why we want to talk about it. This is actually an example of what's called Bayes' theorem. Okay, so this is an example of what's called Bayes' theorem. And so what we can do is, we'll talk about Bayes' theorem in a second and how we can involve Bayes' theorem formally. So I'm going to wait to formally define that. But there's a reason why we want to talk about this. So I want to think about a few things. One is I can just think about straightforwardly, we can just use our formula that we have, probability of A given B. We have a formula for that. So this is going to be the probability of B1 and R2 divided by the probability of R2. And we've already computed these numbers. We can just plug them in. Everything is fine. We're going to end up with, let's see, 7 over 30 divided by the probability of R2 was 21 over 30. And so if we cancel the 30s, this will be 7 over 21, or 1/3. So there's a 1/3 probability that the first ball is blue, given that the second ball is red. I want to notice that knowing whether or not the second ball was red or not actually influences the probability that the first ball is blue, because the counts could change. If the second ball was red, that makes it more likely that the first selection was blue, right? Because if the first selection was red, there would be fewer reds on the second draw. So knowing what happens later actually can affect what happens earlier if we think about it in this kind of reversed order way.